Okay, this is a pretty epic problem. There's nothing is that everything's difficult in it, including these slightly difficult angles. This wire is. Let's just work it through. Find the tension in the wire. Well, to find the tension in that wire, we need to use the concepts of static equilibrium. Forces in the x direction. Well, that wire is pulling on this beam. This beam has its own weight. It wants to fall down. The wire's holding it up. It pivots around this point. It is in static equilibrium. So with regards to the beam, the net force, the x direction 0. The net force in the y direction is 0, and the torque is equal to 0. So if we just consider, we've set up our diagram, we haven't identified all the forces. That's before we even start working with these equations of static equilibrium, we need to identify our forces. So this tension, and the object of study is the beam itself. So we look for the points of contact. The points of contact are down there. There are going to be forces on this pivot. If there are forces on this pivot, they're going to have an x dimension, or an x component and a y component. I don't know what either of those are. I don't know their direction. I don't know their magnitudes. They could be 0. They could be negative. I don't know right now. I'm just putting them there, and I'll solve for them. There's a point of contact here. So we look for, and I'm going to call that the tension. And this also has a weight, so the weight of the beam itself. The beam has a total length L, and so it has a center of mass. Because it's a symmetrical beam, it'll have a center of mass at half the length of this beam. And gravity, there's a force of gravity equal to its weight, which is mg. Whatever its mass is, weight equals mg. So we know that. So there's a force of gravity on any object with a mass. It has an effect basically at its center of mass. You can assume the whole beam is just a point right there and is pulling down, wanting to torque it in the clockwise direction. This beam is holding it up in the counterclockwise direction. But it's not slipping to side, so we know the net force in the x direction is equal to 0. And the forces in the x direction, well, there's f of x pushing it out. W has no force in the x direction, but this tension is doing two things. This tension is, as far as the x dimension goes, this tension is pulling up at an angle, so a lot of the tension force is pulling it directly in. So that is Tx, and a little bit of the tension is going upwards too. So that tension is slightly up, and it is quite a bit, so slightly vertical and quite a bit horizontal. So and that is in the negative direction. So now it's starting to get messy, but if that's 30 degrees and these are opposite interior angles, I know that that is 30 degrees. So I actually know the angle inside here is 10 degrees. So if that's my hypotenuse and my components are the opposite and adjacent sides of 10 degrees, I'll make a little note here. I do know that ty is equal to, it's the opposite side, so that's sine of 10 degrees times t, whatever t is. I don't know what it is right now. And I do know that the horizontal component is equal to cos 10 degrees t. So t can be split up into a vertical component and into a horizontal component. This horizontal component is balanced by this horizontal component at the pivot point. So this leads to a very simple first equation saying that the horizontal tension in x is equal in magnitude, opposite in direction to the force down there at the pivot point. Both of those are unknown. That's not going to help me right now. How about the y direction? What are the forces in the y direction? They're going to add up to 0 because it's not accelerating up or down, so there's no net force. There's a force in the y direction. That's the weight. It's downwards too. So if I remind myself of my coordinate system, there's y, there's x. That's positive to the right, positive upwards. Also, I might want to remind myself of the torques. That is a negative torque, and that is a positive torque. Actually, no, that's all the same direction if I did. That's a negative torque. That is a positive torque, all the way around. Might be easier. Yeah, I'll just leave it. Okay. So, force is weight downwards, negative, that's a vertical force. There's a little vertical force here caused by this tension. So this tension is partially pulling up. It's mostly pulling in, but it's partially pulling up. There's ty upwards. And, well, I'm not sure what this is, if that's, but I'm going to put it down there, plus f of y. There could be some force up or down here at this pivot point. I don't know that value. It could be 0, could be positive, could be negative. I don't really know. I'm going to leave this. I don't know this. I don't know that. I do know that. So this has a bit of information in it. Sure, I'll restate it here. This is weight has the same magnitude as ty plus f of y. Okay. Torque, net torque is equal to 0. The pivot point's there, so these forces don't have any torque because their lever arm is 0. There's a torque here caused by the weight. And you know what? I'm going to use, remember torque has two forms. You can consider the perpendicular force times lever arm, or you can consider just leaving the force alone and thinking about what the perpendicular lever arm, what the perpendicular component of the lever arm might be. I think on a previous problem we broke this up into components, but I'm going to show you how you could, I could leave the weight alone and instead break up this lever arm into, there's our lever arm here, and it has kind of a portion parallel to the force and a portion perpendicular to the force. So this lever arm, this is the x component of the lever arm. So I'm going to put L over 2 in the x direction, and I'm going to put L over 2 in the y component. That's 30 degrees, so it's pretty easy to figure out what the torque caused by this force is. it's the weight times the component of the lever arm that's perpendicular to the weight, and that would be this one, L over 2x, which is equal to, it's the adjacent side to the angle that I know, cos 30 degrees times the hypotenuse, which is L over 2. Cos 30 degrees, L over 2. And I could have just kept L over 2 and then broke up this weight into a perpendicular and parallel component like we've done before. Any student is welcome to do that, and they'll come up with the same, with a mathematically equivalent statement. In fact, I will do it now, just to show you what would have happened. And actually, it's probably a useful illustration. I could have said perpendicular force, this perpendicular force, that this would have been theta there, and then I would have used weight perpendicular to L over 2, but weight perpendicular is equal to the weight times cos of 30 degrees, and I would have had exactly the same statement. What I would have had is cos 30 degrees times the weight, L over 2. The full lever arm. So it's the same thing. You should use the perspective of your choice. Okay, unfortunately things aren't they're not quite as easy up here. The tension is at an odd angle, and I think I'm going to say, and notice I've already broken up the tension into components, but that was relative to horizontal and vertical. Now to figure out torque, I need to think about what this tension is doing, how this tension is either parallel or perpendicular to the beam. So relative to vertical and horizontal, the tension can be broken up into Tx and Ty, but relative to the beam, which is at an angle, I can break up tension into the perpendicular part of the tension. So the tension out here at an angle is partially twisting, and it's partially, this is the parallel portion of the tension, it's partially pulling this beam into the wall. All right, now it's, let's see, what's the time? I'm going over time, I better stop now.